Last week we were working on work energy theorem, which says that work is a change in energy. Okay, so in this question, we are changing the kinetic energy of a ball that has been put into a rubber band that's been stretched. So when I stretch a rubber band, okay, in order to stretch it, I have to exert a force. When I exert the force on the rubber band, I change its shape. That is, I make it longer. So I exert a force through a distance, and that's one of the formulas that calculates work. Okay? The other formula that calculates work is change in energy. In this case, we want to find out how much the work that I've done on the rubber band will change the kinetic energy of this 0.125 kilogram ball. Okay? Because when I stretch back the rubber band, what kind of energy do I give it? I give it potential. And as soon as I let it go, that rubber band will exert a force through exactly the same distance on the ball, essentially conserving all the work that I did, okay, by putting it into the ball. Once the rubber band is snapped and the ball leaves the rubber band doesn't have any energy anymore because it's all in the ball. Okay, so everyone kind of follow the chain of events. Okay, so we've got that this will equal our change in kinetic energy. So we can simplify this. It looks like this: force times distance equals 1/2 mvf squared minus 1/2 mvi squared. This is the formula for kinetic energy from last week. Okay, this would calculate the final kinetic. This would calculate the initial kinetic. Now, when the ball is sitting in the rubber band, how much kinetic energy does it have? 0. Okay, so we don't even have to worry about this part because it's 0. So I'm left with the force times the distance will give me the final kinetic energy of the ball, which is true in a perfect world. Okay? In the real world, it's not true because the rubber band makes sound when it snaps. There's going to be some heat generated and some energy will be lost to those kinds of things. But we only deal with the perfect physical world because it's way easier. Okay? All right. I want to get the final speed of the ball, which is VF. So how do I get VF by itself? Okay, what do I divide? Half of m, right? I got to bring the 1/2 and the m over to this side. Okay, that gets me VF squared. I just want VF, so what do I need to do to both sides? Square root. All right, so the square root of this will equal VF. So when I plug in my numbers, VF will be the square root of the numbers we were given here. So 60 newtons was our force. We stretched it 0.85 meters. Okay, and then we divide that by half of the mass, and the mass was 0.125 kilograms. All right, so we're going to have 60 times 0.85 divided by 1/2 times 0.125. Whoop. Okay, and then we take the square root of that. All right, so we get 28.6 meters per second, which is pretty fast, which is why you shouldn't aim a slingshot at somebody, because you could take their eye out, because that's really fast. And that'd be dangerous. Okay. All right, so everyone kind of follow what we did there. Basically, all of the work energy theorem questions we do will set up like this one. Okay? Work will equal either the change in kinetic energy or it'll equal a change in potential energy, one or the other. Okay? So that'll be initial or final minus initial equals F times D. And then you're just going to be manipulating to find some part of that. Final speed like we just did there. Maybe it'll ask you for the force that was used, how far the work was done over, so the distance, the height of the object, something like that. Right? That's what we're going to be looking for with these kinds of questions. So I want you guys to try this one. It's very much like what we just did, except this time you're looking for the force instead of the final speed. So in this question, the tractor is pushing the rock. Are we changing the energy of the rock by pushing it? Okay, it's going from rest, so it's not moving at all. And when the tractor is done pushing it, it's moving at 4 meters per second. Have we changed its energy? Yes. What kind of energy did we change about it? It's kinetic energy. All right. So anytime there's that's kind of one of the first steps we want to have here is when we're looking at a question, first off, identify, is there energy being changed and what kind is being changed? All right. In this case, because it's going faster, it's kinetic energy. If this was a question about lifting something up to a specified height, then I'd be changing its potential energy. Okay. Either way, work is being done because the mechanical energy, either kinetic or potential, is being changed. All right. So we want to write down that work is changing, in this case, the kinetic energy of the rock. All right. The givens that we have, we know the distance over which the rock is pushed. It's 25 meters. We know the initial speed of the rock is 0 meters per second, and we know the final speed of the rock is 4 meters per second, and we know the mass of the rock is 550 kilograms. Okay, so that's what we know. If I'm looking at work being a change in energy, the formulas for work are force times distance, and to calculate the change in energy, I would go 1/2 mvf squared minus 1/2 mvi squared, but since vi is 0, do I need to bother with that part? No, because it would be 0 anyway. All right, so I'm looking for what force was exerted. So I'm looking for F. How do I get F by itself? Divide by D. All right, so the force used by the tractor to push the rock will be 1/2 times 550 kilograms times 4 squared divided by 25 meters. Okay. So 0.5 times 550 times 16, okay, divided by 25 meters. All right, so they used 176 newtons worth of force. Okay, everybody all right with what we did there? Okay, anytime you read a problem, identify, is there work being done? So is there a force, is there a distance, or is there a change in energy? Any one of those says that yes, indeed, okay, work is being done. Okay, so in this one, a person is carrying something from one height to another. You need to calculate how much work is done. This one's actually a little easier because you have less manipulating to do. Okay, so read the question carefully and figure out what kind of energy is changing, and then calculate the work. Give you a couple minutes on that one. Okay, I'm seeing a lot of people going off here, so we're going to walk through this one. Okay, in this question, are there any forces given? Say anything in newtons, or say the force used is this much? Okay, so we can't calculate work using force times distance in this question at all because we don't know what the force is. Okay, but there's another way to calculate how much work is done. Okay, and that is that work is a change in energy. What kind of energy are we changing about this package? It's potential energy. All right, so we've got work is a change in potential energy. All right, now what that means for us is we got to calculate the final potential energy and subtract from that the initial potential energy. Right? This is why I said there's less manipulating to do in this one than there was in the others, because I don't have to do the force times distance part. I don't know what the force was, and it doesn't matter. They only asked me to calculate the work, okay? Calculate the change in the energy of the package. So our givens are that this is a 10 kilogram package, okay, and that we are going from a height of 30 meters to a height of 100 meters. Okay, and we're just looking for how much work is being done here. All right, so I'm just going to plug in my numbers. The mass of the package, 10 kilograms, times 9.81, times the final height, 100 meters, minus 10 kilograms times 9.81 times the initial height, which was 30. How did I know to use 9.81 for g? Right, that's acceleration due to gravity. And if it doesn't say otherwise, we assume everything's happening on Earth. Okay, now, if you're like mathematically minded, you probably would notice that you could have also shortcut this to just say 10 times 9.81 times 70. That's fine too. Okay, that's essentially the force of gravity times the distance. You could have done it that way. If you didn't realize it, don't worry about it. You didn't have to do it that way. Okay, so what we got in our calculators here is 10 times 9.81 times 100 minus 10 times 9.81 times 30. All right, so this is going to require 6,867 joules worth of work, because that is how much more potential energy the package will have on the 10th floor. Okay, so the questions are not like mathematically difficult, but they are contextually difficult. We have to make sure we're reading the question carefully, identifying what kind of energy is changing so we know whether to use mgh or 1/2 mv squared, if we need force times distance or we don't, okay, those kinds of things. Those are the things we have to get out of the question, okay, out of reading it out. So there's a little bit of reading comprehension to do here, right? At least though it's all cut and dry, okay? It's not like, what's the theme? Or did Johnny really mean what he said? Okay, it's not like in English. Okay, it's more concrete. Okay. Okay, so on this one here, we got a bulldozer that does 7,500 joules worth of work. So they told us how much work was done. Okay, in pushing a truck from a speed of 2 meters per second to an unknown speed. Okay, if the truck has a mass of 2,500 kilograms, what is its final speed? All right, give you a couple minutes on that one. First thing you need to figure out, what kind of energy is being changed by the 7,500 joules worth of work that was done. Okay, so let's have a look at this one. This one's also a case where I don't have to use force times distance because they already told me what the amount of work is, right? They gave me that number, so I don't have to worry about that part. Okay, what kind of energy is being changed in this one? Kinetic. It's speeding up, right? It's going from 2 meters per second to some unknown speed, right? There's no mention of it going uphill or being lifted or anything like that. All right, so we got here then that work is going to change the kinetic energy of this truck. Okay, so what we know here is that we have 75,000 or 7,500, sorry, joules worth of work being done. Okay, we have a mass of 2,500 kilograms. We have an initial speed of 2 meters per second, and we have an unknown final speed. Right? That's all the stuff that we know. All right, so if we're looking at work being a change in kinetic energy, that's going to mean work equals 1/2 mvf squared, so our final kinetic energy, minus our initial kinetic energy. I'm trying to isolate this term. Okay, I want to know what VF is. So right now, what should I do with the 1/2 mvi squared? Add it to the other side. Okay, remember, work is the change in energy. So if I take the initial energy, which is the 1/2 mvi, and add it to the change, that should give me the final. Agreed? Right, so that's the first step we're doing. We're adding the 1/2 mvf squared, or mvi squared, sorry, over to this side. All right, so we've got the work plus 1/2 mvi squared equals 1/2 mvf squared. Now is it easier for me to isolate vf? What do I do to get vf by itself now? Right, divide by 1/2 of m. All right, that doesn't cancel the 1/2 of m. Okay, sometimes people make that mistake. There's an addition operation on the top, so I can't cancel that. And then I need to get vf, so I'm going to square root. So this one's fairly involved in terms of manipulating. All right. Now, I just need to plug in my numbers. Okay, I was told the work was 7,500 joules. I'm adding that to the initial kinetic energy, so 1/2 times 2,500 times 2 squared divided by 1/2 times 2,500. Okay, all square rooted. That will give me my final speed. Okay, so we got 2,500, and then we're going to divide that by 1/2 times 2,500. Whoop, not 250, 2,500. All right, and we get 2. I did something wrong. I subtracted instead of added. Yeah, that doesn't make any sense. There was a few people who had the right look on their face. Okay, when I looked out there, there was a few people going, "It doesn't seem right, Coder." Never doubt yourself. Okay, if I do it wrong, it doesn't necessarily mean. Okay, all right, and I just about did it again. I put a minus in there. Plus 0.5 times 2,500 times 4. That's better. That's better. Okay, and then we're going to divide that by 0.5 times 2,500. Okay, and then we're going to take the square root of that. Okay, so it's going to reach a speed of 3.16 meters per second. Okay, so it is speeding up. Okay, but it's a big truck. It's a lot of work, and we don't change its speed very much. Okay. All right, that's probably as tricky as they would get. Okay, I don't think you would get one trickier than that. Okay. All right, now, like I say, those are about as hard as they get. I'm going to give you a chance to work on a few easy ones, but first I'm going to give you about a 5-minute break. Okay, then we're going to work on some easier ones. Okay, so take 5 minutes, check your messages. Okay, so let's quickly talk about question number 1 here. Okay, so in question number 1, they tell us there's 32 newtons worth of force lifting a box 3 meters. So they gave us force and distance as well as height. Okay, there's actually 2 different ways to look at this question. Okay, the 2 different ways to look at it. Sorry, I have a whole bunch of other examples. We'll go over a different day here. Okay, so the other, so we can look at this 2 ways. We can say that work is force times distance and calculate it that way, or we can say that work is the change in potential energy. They'll arrive at the same answer because we're talking about the same thing, okay, lifting this box up, okay. So if I go force times distance, that's going to be 32 newtons, okay, times 3 meters, right? When I do that, I get 96 joules. Okay, to do this with EP, I would actually have to know the mass, which they didn't give me, but I could figure out. We haven't gone over how to do that. Okay, so I'm actually not going to solve it this way. Okay, but when they say calculate the potential energy of the box, why is it the same number? Right, the only reason the box has potential energy is because it was lifted. Work was done on it. 96 joules worth of work means it gained 96 joules worth of energy. Okay, that's why that works out that way, because work is not only force times distance, it is also the change in potential energy. That's why they're the same number. Okay, that's all that question is really there to illustrate to you. It's not there to test your mathematical skills. All right, how are we doing on question 2? How many people have done question 2? Okay, any trouble with that one? Okay, let's keep going then. Okay, so let's have a look at number 3 here. Or sorry, number 5 and 6 here. Okay, so in question number 5, we have to calculate the force required to test the rubber band here. Okay, so we know it's stretched 10 centimeters, but here's where we have to remember the fundamental units for a joule. A joule is a kilogram meter squared per second squared, which means I can't use centimeters for distance. I have to use meters. That's okay. If you were getting a number that was different from this by a couple of decimal places, that would be why. Okay, so our distance here is 0.1 meters. Okay, the work done, or the energy, is 320 joules, and we're looking for the force. So force equals 1 work divided by distance. We just manipulate the formula. So we got 320 divided by 0.1, which is 3,200 newtons. All right, for number 6, okay, the rubber band has a mass of 0.02 kilograms, so 2 grams, okay? Or sorry, 20 grams. All of the 320 joules worth of work that were put into stretching it are now going to be kinetic energy once he lets it go. Okay, so what we're saying here is that the kinetic energy of the rubber band is 320 joules, and that can be calculated by going 1/2 mv squared. Right, so all I have to do now is solve for v, and I'll have the 179. So I just divide 320 divided by 1/2 times 0.02, okay, and I'm going to get, square rooted. That'll give me v, and I'll get 178.9 meters per second, which would definitely take your eye out, possibly leave a hole coming out the other side. That's pretty fast, okay? You wouldn't want to get hit by that. Yeah, it's half the speed of sound, okay? Mach 0.5, okay? Pretty bad. You wouldn't want to get hit by that, okay? All right. Any other, sorry, number 3, right, Easton? Okay. Okay, so if we're standing on the gym floor and we're going to jump straight up, okay? I'm not going to take a run at it, just going to jump straight up and dunk a basketball, okay? He has a mass of 70 kilograms, okay, and jumps straight up to a position where they've gained 800 joules of energy. All right, what kind of energy does he have if he's jumped upwards? Potential energy. So his potential energy at this point is 800 joules. Okay, we're looking for the height of his jump. So really, this is just an EP. Whoop, that's too many slashes. Equals m times g times h, and we're just solving for h. So we divide both sides by m times g. Okay, we're left with h, so we go 800 joules divided by 70 times 9.81. That has to be in brackets on your calculator, okay? And that should come out to 1.16 meters, which is an impressive vertical jump. Okay. 1.16 meters is like 46 inches or something like that, okay? Somebody could jump straight up in the air. Strictly vertical leap, yeah, that's pretty impressive. Okay. All right, any other ones? All right, keep her going then.